we've got another physicist, so there's 3 up until now, which is great for these days. And the next talk is by Dr. Kirsty Kitto, and the title is Quantum Cognition, Do You Have a Quantum Mind? And maybe she'll touch on whether quantum minds can explain any of what we've heard about from Ajahn Brahm. Kirsty models the many ways in which humans can interact with information and how this can change as a result of the different contexts in which people find themselves. She's working towards providing unified mathematical and computational models of this phenomenon, which often results in apparently complex and unpredictable behavior. Kirsty's background, she's got 4 degrees. She's got a Bachelor of Science in Theoretical Physics from Flinders. She's got a Bachelor of Computer Science, again from Flinders. She's got a BA, a Bachelor of Arts in Maths, Philosophy and Spanish. Guess where from? Flinders. And she has a PhD in Theoretical Physics from, you guessed it, Flinders. She's collaborated on projects with people from a wide range of fields, including physics, experimental psychology, cognitive science, computer science, social psychology, and computational linguistics. She was an investigator on a European Framework 7 Marie Curie International Research Staff Exchange Scheme, which brought together physicists and experts in information retrieval to work on the problem of incorporating contextual models and into models of information access and retrieval. She says about herself on her Twitter byline that she's a habitual crosser of disciplines, a divergent thinker who sometimes gets things done. Her other interests, I believe, are climbing, permaculture, and saving buildings. And just to say, her name, Kirsty, is the Scottish variant of Christina, which means Christian. So, Kirsty, over to you.
So thanks, Scott, for telling me what my name means, which I did actually know, and I remember being terribly disappointed when I learned that when I was a child. It seemed like the most boring interpretation that I could have, but that's alright, I've grown to like it anyway. So I thought I might give you all a bit of an indication of what my journey has been before I even start talking about what I wanted to talk about today. The multiple degrees was really just a sign of someone who doesn't really know when to stop. I just got interested in a lot of different fields, and really the thing that I find most interesting in science is that concept of crossing disciplines but with depth. So you need to know enough about fields to be able to do interesting things within that field. But when I actually started looking for my first postdoc, having really, with my PhD, looked at a lot of models of complexity, how can you develop new models of very complex systems? I ended up with an information retrieval group, which is the Marie Curie Fellowship. So I went to work with Peter Brusa, who's an information retrieval expert, who had actually got a discovery project that was looking at modelling semantic space using quantum mechanics. And the reason why he put that discovery project in was because the formalism in information retrieval was looking very similar to the formalism of quantum mechanics. And so we spent some years playing with that. Then we started working with some experimental psychologists looking at memory and language and recall. And so I spent a couple of years collaborating with them and got my own fellowship. And then started getting interested in attitudes, and so ended up in social psychology. And each time I've been moving these fields, it's like, oh no, there's so much more reading. But it's incredible how unifiable a lot of these concepts can be as you move through the disciplines. So even now I'm learning all about learning because I've taken a secondment to look at learning analytics and developing learning analytics at UT. So it's incredible how far a physics degree can take you if you're interested in looking at the world in different ways. And following on from the previous talk, really approaching new fields and new ideas with a degree of respect. I think physicists have a bit of a tendency to go barging into fields sometimes and not listen to the amazing things that people have learned in these other fields, and I think it's really important for us to be very respectful of them across the disciplines. So, for example, experimental psychology has the most amazing experimental protocols. Just phenomenal, absolutely impressive. So I've learned a lot there. So, what are we going to talk about today? Wrong way. Sorry. Okay, I exist. So what I want to talk about today is a field of research that I've been working in, and there's a lot of other people who've been working in this area. Essentially, there's been a lot of work in trying to adapt the formalism of quantum theory towards modelling other things, and in my case it's complex systems, but today we're going to focus on cognition because that's a lot of the area where I've been playing a lot. So, there's two questions that I want you to keep in mind. Now, I've been told that some of you physicists and some of you have no physics knowledge or very little physics knowledge. The blue slides are the ones where I want you all to feel very happy. There's going to be some white slides, which will get a bit more technical, but not too much more technical. So the physicists who want more details, feel free to come and talk to me afterwards, or send me an email and I can flesh out details for you with whatever you're interested in. But the people who are worried about getting lost, if you do start getting lost, just wait for the next blue slide, okay? that would be my advice. So, the two questions I want you to keep in mind are, what's a quantum system? And this is very much following on our last talk, okay? So what exactly is a quantum system? And if you think about a lot of the paradoxes in quantum mechanics, they stem from the fact that we don't know what a quantum system is fundamentally. Schrodinger's cat is a classic example of a thought experiment that indicates that we don't know where the microscopic sort of turns over or transitions into the macroscopic. Yeah? So there is a problem with measurement in quantum theory that we've never really resolved all that well. Depending on your interpretation of quantum mechanics, you may disagree or agree with me. But I mean, to me, the fact that there's so many interpretations of quantum mechanics suggests that we never really kind of worked it out, did we? And in fact, you know, the different interpretations could be seen as people having different amounts of baggage that they're willing to surrender. So, you know, if you're happy with many worlds interpretation, that's because you're quite happy to believe in a universe that has a whole heap of stuff you never see. If you want to play with spontaneous localization theories, that's because you're not so happy with relativity. Like, you know, it depends on what you consider important to keep. And the reason I think we need to be thinking about what a quantum system is because actually we can push our understanding of what a quantum system is by trying to break the formalism somewhere else. So let's go and break it in cognition, see how far we can push it, and what we can learn in applying our formalism somewhere where it really just shouldn't be. Well, maybe it should, maybe it shouldn't. So, over here we've got Descartes, Descartes' idea of a quantum model. And this is, again, that concept of mind and body, or mind and brain. Like that dualism that we've had creeping into our models of cognition for a very long time, I find a bit unsatisfying, and this does come back to the last talk. I'd like to think that our models could get better, and with better models we may not need to think of the mind and the brain as different things, but actually it's our modelling that's failing us. That's where we need to improve. So that's what that's what I've been trying to do throughout my research career. So, first question. What's a quantum system? So the kinds of systems you think of when you think of quantum mechanics would be, collisions in Large Hadron Colliders, or, quantum dot experiments, or, corrals. And what are you going to, where are you going to draw the line on what a quantum system is? Quantum systems can get pretty big. They can, scale up to large systems, very large systems. How large can they be? Where's the line? So let's think about this question a little bit more. Because there's people doing stuff like this. So there's a lot of people applying the quantum formalism quite inappropriately. You can't just go around saying, well, it's quantum. because, decisions were random or blah, blah, blah. You need to have some sort of systematic reason why you might be using this formalism and some sort of understanding of whether or not it's appropriate. So there's a lot of different businesses, for example, they're full of it. You see a whole heap of people going, oh, it's a quantum business, or oh, it's a emergent something or other with very little evidence. And I do believe in evidence. We need some evidence. We need to run experiments. So, two effects that I consider important and absolutely key to whether a system is quantum or not. The first one is interference. So if you have a wave, or you have a system of waves, and they bang into each other, or they cross over with each other, then you'll get a series of peaks and troughs in those waves. So you've seen that in the ocean, you've seen it with light, you've seen lots and lots of different interference effects in your life. But the problem, from a quantum perspective, is that you get a bit of both. So if you have a particle and you throw it at a screen, you'll get a spot. If you get a particle and you throw it through a slit at a screen, you'll get a line of spots. If you get a particle, just one particle, and you send it through a double slit experiment, you'll get one spot. That's fine. But if you do lots of them, you'll get your interference effect building up. So the question you need to ask yourself, if you're not a physicist, if you're a physicist, you've seen this since first year or even before that, but the question you need to be asking yourself if you're not a physicist is, how can a particle interfere with itself? So if you get a tennis ball and you throw it at a screen, and you get another tennis ball and you throw it at a screen, that's not going to make a dark spot. It's not going to make something that didn't happen. So the question becomes, how can you get these dark bands while still getting these spot effects? This is a key quantum effect. And in fact, to me, this encompasses the measurement problem of quantum mechanics. So, how do you explain the fact that you get both interference and spots? Single events in the quantum formalism are very, very hard to describe systematically. Okay, so, keep an eye on time. Entanglement is the other key effect for me with quantum mechanics. So entanglement is a very interesting one because it starts to challenge relativity, brings us into an uneasy kind of peaceful coexistence, is the way Shimony talks about it. What we've got here is a picture from a fairly modern experiment that's been run out of Geneva, where you can actually entangle particles, send them down optic fibres to two towns, 18 kilometres apart. And you end up with these particles displaying effects that essentially imply that what's happening over here is affecting what's happening over here. Okay, so over 18 kilometres. Now, we'll explain a bit more detail about that. What you do, and what John Bell did when he tried to formalise, and actually this is back to our earlier discussion about Einstein and Bohr. Bohr, when he proposed quantum mechanics, or Bohr when he started talking about quantum mechanics, had a very, almost mystical understanding of what quantum mechanics was. And the thing I really do appreciate about Einstein was that he wanted to understand what was going on. He wanted a model. And that's very much in my way of thinking about the world. I like models. So what Einstein did was he proposed a thought experiment with Podolsky and Rosen, which essentially talked about if you entangle two particles, so if you essentially if you let them interact with each other, then take them apart, you can do measurements on this side of this particle over here, and they could actually be experiments that you're not allowed to do together. So you could measure position over here, you could measure momentum over here, and you can reason counterfactually about what might have happened over here on this particle. So you can actually know more about your particle than you're allowed to know according to the formalism of quantum mechanics. Now this was an impossible experiment to do, but it got formalised by Bohm, and there was a whole history that went over, from the 1930s onwards. And in fact, the experiments in their first run got, the very nice run got done by Aspect, And what they found was that fundamentally the predictions of a classical, well, the predictions that you can't know about this particle, you can't know everything about this particle, are actually satisfied by your quantum system. So the reality satisfies quantum predictions rather than classical predictions. So for example, looking at the formalism, and again, if you don't want to know about formalism, just ignore me until we get to the blue slide in a minute. You can talk about hidden variables that you might have proposed that would explain the outcomes of your experimental scenario. But these are ruled out by experiments. So the predictions of a classical theory are for these straight lines. As you rotate your detectors, you'll get a certain outcome. Quantum systems follow the curved line, and actually experiment follows the curved line too. So the question that I find very interesting about this is, well, if we go back to this experiment, how far apart can that be? And in fact, Wheeler proposed a thought experiment where you do these experiments over the entire universe. So you can conceivably entangle a particle and send it to the opposite ends of the universe. So quantum systems can get quite big. There's obviously problems with maintaining your coherence, maintaining your entangled state. But you can get pretty big. So this brings us to the question of, well, how big can quantum systems get? And again, this is why I want us to be thinking about, well, what is a quantum system exactly? Because we don't actually have a point where we can draw a boundary. Right? So we don't know where that line between a quantum and a non-quantum system actually falls. So why wouldn't we be able to start thinking about modelling something like cognition? There is no a priori reason. The quantum formalism doesn't forbid us from using the quantum formalism to model cognitive systems. Okay, so that's the motivation from a physics perspective. Let's go off and think about cognition for a while. So there's lots and lots of models of cognitive processes, lots and lots of different cognitive processes. In fact, the exciting thing about psychology is how much data there is and how ununified the models are. And from a physics perspective, that's just like, oh, what? I could actually unify things here. That's exciting. You think about how difficult it is to unify in physics. A lot of that stuff's been done already. Whereas psychology is full of data with a whole bag of models and no real indication of which model you should use when. That's blue sky research in a whole amazing way. So that's how excited I get when I start moving into psychology. You could be Bayesian, you could do linguistics. Here's a sort of linguistic approach to thinking about language. You could, you could go Bayes nets and talk about sort of people's understanding or their reasoning uncertainty. Here's our quantum model over on the left. Here's an attitude model. So this is a heuristic likelihood model that someone's implemented computationally, and here's another sort of neural network approach. So, there's a million different types of models out there. Some of them are a bit more widely used, so dual process models are very common in psychology. Bayesian models, very common in psychology. Vector space models starting to become more and more common, and this is where the quantum approaches start coming in. So how should we model cognition? Well, the original sort of thing that people would do is use classical probability. So, humans are pretty unpredictable. They do weird stuff all the time. It's kind of the problem with psychology at the same time as being the exciting thing about psychology. The big problem with psychology is if you have a bunch of humans in a room and you ask them to do something, they're never going to do what you really wanted them to do or what you thought they'd do. There'll always be someone doing something that you thought was impossible, whereas electrons tend to be a bit more predictable. So really, if you're thinking about a classical probability model, really what you're doing is you're modelling uncertainty as a lack of knowledge. So I have a system, I know all of its states essentially that it could be in or could obtain generally. I may not know them all, but I could in principle know them all. And when I'm measuring a system, the uncertainty comes from the fact that I don't know what state that system's in. It doesn't come from any kind of interaction necessarily. Like, so really what I'm doing is I'm looking at the system. I don't know where it is or what it's doing, but I know it's got an objective state and I measure that. Yeah. And you get a whole stack of axioms out of that. So, for example, probability ranges from 0 to 1. You get, certain events which have a probability of 1. You get a whole heap of nice mathematical infrastructure out of having that kind of system. Okay, now, the question we might ask ourselves is this what humans do? So, let's try a few things. Alright, so, I want you all to partake in my experiment. Okay, so, you have to promise to partake. So, Linda, she's, 31 years old, single, outspoken, very bright, majored in philosophy, blah, blah, blah. What's more probable? I want you all to close your eyes for a minute, and I want you to put up your hand if you think it's more probable that Linda is a bank teller. Okay, open your eyes. Keep your hands up if you had your hands. Okay, so that's how many people think that. Okay, so how many people think it's more probable that Linda is a bank teller and active in the feminist movement? Hands up, be honest. Okay. Anyone want to tell me what's wrong with that? Yeah? Ooh, yeah. Okay, you just all violated classical probability. Call yourselves physicists, Alright, so, and this is the thing. You could do this to a room of mathematicians. You could do it to a room of statisticians, and they'll give you a bigger probability, or you'll have a stack of people saying that it's more likely that she's a bank teller and active in the feminist movement, okay? Now, and actually, probably you guys did a little bit better than your standard, because, there are quite a few people who know a bit of maths in the room, so they are thinking about this a little bit. So yeah, generally with a normal audience, you'd get about 85% of people essentially saying that the smaller event is more likely to happen, okay? Now, is that wrong? Is this you guys being irrational? Or is this a case of our formalism being inappropriate? Because if we go back to that question, from a classical perspective, sure, it's not that likely that Linda's doing the more specific thing. But from an actual, just psychological perspective, it's actually quite possible that the second one is more likely. So is it a case, yeah? Absolutely. No, they're not. But the question is the problem is, are we thinking about this scenario from the formalism of classical probability, or are we going to think about this problem from the perspective of psychology? Yeah? And so what you have, and this is this is where things like economics come from. Economists are constantly bashing us over the head, telling us how irrational humans are. But actually it's got probably a lot more to do with our mathematical formalism being the inappropriate one. And we need a better mathematical formalism. Yeah? So, so this is known as the conjunction fallacy in psychology. It's very well known, Tversky and Kahneman. Kahneman got the Nobel Prize, Tversky died before he got it, but these are really well-known sort of effects. If you go looking on Wikipedia for fallacies or what would you call it? Oh, wait, I can't even remember. But you can find a whole list of human reasoning fallacies that goes for about 30, 40, 50, 60, I don't even know how many of them there are, there's millions of them. So let's try another experiment. Oh, wait, yeah, here we go. So for example, people have written books about this. You could write books on how predictably irrational humans are. Kahneman's written a whole book about all of these different fallacies. You can even play a bingo game about people being irrational in meetings, so you can take that along to your next meeting and see how irrational people generally are just in a meeting context. And there's given the current kind of political climate as well, the constant warnings of climate scientists that have been going on for how long could be seen, and our general ability to ignore them could be seen as quite irrational as well. So, humans are often irrational. Is this a case of they're irrational, or is this a case of our formalism is the wrong formalism? That's the question I want you to go away with. Let's try another experiment. Oh, no. Oh. Do I want that? Oh, yeah, okay. Here's another example, but I'm going a bit slow. So, sure thing principle. If an event in two contexts is more likely, whatever the context, then it's a sure thing that you should be doing something, for example. So, for example, let's just think about Alice and forget about the formalism unless you want to care about it. Alice is wondering whether she should sell her shares. We know that share prices drop after an election. It's actually very common. People know about it. So Alice, if she was behaving rationally, she should be selling her shares. But it's well known that people wait till after the election. So people behave irrationally, all the time. Here's another experiment. Form your first association of mankind. Just form an image in your head. Everyone got an image? What kind of images do people think of? Caveman, yeah, cool. Anything else? Yeah? Yeah, you can't be wrong. This is what I mean about humans. They're messy. You say whatever comes to mind. Right? So this is a word association experiment. So what? Sorry? A gentle person? Yeah? So he's the caveman who's developed some technology. He's got stuff going on. Yeah? Well, this is the one that sprung to my mind. I think of stuff like that, so I think of like a whole bunch of humans, they're all milling around and I just want to get out of there, and you think about the associated technology that went into building that society, and so there's a whole heap of associations that come with seeing that word pairing together, yeah? Mankind, we think of whatever you think of, but it's something relevant. Let's try it another way. What do you think of when you see that? Same thing? So the associations are different, yeah? I was just trawling Wikipedia for an image, and because of the previous talk, I actually, there you go. So there's associations, and actually your context will affect the association you come up with, won't it? So the fact that I knew there would be a Buddhist monk talking before my talk kind of went, oh, okay, well, and this is the thing that came to my mind when I was trying to come up with an image. So human word associations, what we retrieve from memory or how we think of language is highly contextual. It's quite random, but very lawful in a way. So we can try another experiment. What if I ask you all what a pet human is? Anyone want to tell me what a pet human is? None of you have probably even heard of that concept before. Anyone want to hazard a guess? Bunnings? Did you say Bunnings? So Bunnings is full of pet humans, or what's a pet human in Bunnings? I don't even know. Yes. Any other associations? A child? A gigolo? Has anyone said something that made no sense to anyone? It's actually quite easy to understand these associations, yeah? You've never heard of a pet human before, but you can understand someone else's use of language here. That's quite interesting. And if I do this experiment, I normally get something like child, robot, slave, the three kind of general senses I get. So there's actually a very lawful behaviour going on here. It's quite a bit more random than you'd get out of a physical system, but it's very lawful. So that's interesting, because that's something I could model. But it's hard. I've been trying to model that for about, 4 years. So, yeah, just because you can see it doesn't mean you can necessarily find it. Okay, so, my slides gone. Bananas, oh well. So quantum probability is another form of probability you could use to talk about human reasoning. White slide, so don't worry too much if you don't want to worry about the maths. The diagram's the important thing. So the diagram is essentially indicative of how geometric probability works. And what this means is that that arrow with the A attached to it, think of that as a state. So rather than having a state as a point in a phase space, say, a state is a geometric structure. It's a vector. And that means you have to be talking about it with respect to some framework, with respect to a basis of some sort, yeah? So if you want to talk about probability in a quantum system, you talk about projections of that state onto some other basis. So you need the representation of the system before you can talk about it. And we do that in physics all the time. We talk about spin in terms of Stern-Gerlach rotations of analyzers. We talk about, what slip the thing go through. Like the representation we use in constructing our physical models of reality are implicitly, if not explicitly, depends on where the person is and what they're doing, incorporating or acknowledging that fact that our measurement is actively influencing the system that we're measuring somehow. Well, sort of. It's very hard, it's a very slippery area, it's hard to actually come to grips with. But what this means is that if you talk about a measurement in two different contexts, you could have very different probabilities or very different likelihoods of things occurring. Now that's kind of cool, because that would mean that, for example, if I talk about mankind, man is providing a context for your interpretation of kind or for the association, whereas if I'm talking about kind, man, the order in which you're processing that information is changing how you interpret that information. Yeah? So that's pretty nice. So really the blue box is about, I can't remember what I did there. It was about essentially quantum probabilities being contextual and active in some way. It's not that you're just finding out what's there, you're actively sort of doing something in performing that measurement. There's an extra kind of aspect here too, in that if you're in a proper quantum system, so in a pure quantum system, the state, we know, will then collapse to the thing that you obtained, yeah? So that collapse postulate is even more important, because if you think about it, once you've thought of whatever you interpreted mankind is, it's very hard to move to the next interpretation without performing another measurement. So you actually almost collapse onto that interpretation. Yeah? Okay, so, oh yes, back to a blue slide. You can breathe easily again. Okay, so quantum cognition is all about, really the game we play as a field is to make use of this adaptive contextual measurement thing, right? So it's about using the formalism of quantum probability to model cognitive processes. There's people modelling biology, there's a whole heap of different stuff people modelling, but I'm sticking with cognition today. And people have modelled a whole heap of different stuff. So if you go looking for the quantum interaction proceedings, they're normally published with lecture notes in computer science. You'll see a whole history of stuff. There's a lot of papers appearing in the Journal of Mathematical Psychology, Proceedings Royal Society B, Psych Review. So there's a history of stuff you can look up if you want more details. The Quantum Cognition book by Busselmeyer and Bruiser. So Peter Bruiser's the guy that I came to QUT to do my postdoc with. That's quite widely available, but yeah, there's a lot more stuff if you want to find out more. Interestingly, and almost in symmetry with quantum physics in terms of how it developed, it's only partially worked out. There's a whole heap of problems in this field. We have no idea about time evolution, really. I mean, if you think about it, when you're starting from physics and you've got classical physics and you're quantizing, you've got things like Hamiltonians and operators and you know what you're measuring. When you're starting in a psychological system, you don't even have that basic formalism set up, which is actually the reason why you're starting to use quantum mechanics, because you're actually trying to develop formalism. But there's the inherent problem of actually even just developing that sophisticated theory when you're starting from a very low modelling baseline. So here's an example. How much time have I got? Oh, yeah. So we're getting to the end anyway, so we'll fly through the examples. So language and memory. So we've already seen some examples of these effects in terms of how they work. Here's another example. Boxer bat. What's a boxer bat? You want to think of it, you want to hold it in your head. And then, is it anything like that? Any of them? I can pretty much predict, so some people will think of it as a boxer dog that has bat-like characteristics. Some people will think of it as a bat with boxing gloves, but they're the two kind of classic ones. Problem is, you go off and run the experiment, and people come up with dumb shit like boxer shorts. And like that's what's frustrating about people. You think you've got it all nailed down, but then they always come up with something else. So it's really hard with people. So this is starting to look a bit quantum-ish, isn't it? Because you could talk about an animal sense or a sporting sense. And what you're doing is you're collapsing your system onto an animal sense and a sporting sense, or well, animal, or whatever, I can't even remember what it was. So that's starting to sound interesting. And actually, you can run experiments on this based on a sort of EPR type framework. And we've been doing this for years. So you can actually, the experimental psychologists I work with, they've spent 30 years collecting word association data. And essentially, if you look at boxer, you'll have probabilities of fighter, gloves, fight, shorts, punt, so you'll actually have a whole sporting sense of the term. You'll have dog sitting there. These word association data was obtained in the US. If you do it in Australia, you tend to see much higher animal, like dog sort of recall. That makes sense too, because that's a context effect. So when you do sort of experiments with word associations in the US, there's a much bigger culture around boxing, and so you'd sort of expect that, wouldn't you? Dog, bat, you can talk about bat and ball, you can talk about, bats as vampires flying in the night. So you can actually model these in vector spaces. People do this all the time in information retrieval. But then you have an interesting thing. When you combine those concepts, which representation should you use mathematically? Should you be talking about a nice separable state? You just use your tensor product and you form it all out and you could separate it back into your brackets. Or should you be talking about an entangled state? Like it's not compositional is what the term you'd use in psychology. So you talk about the state being not non-separable because it's in someone's head. Yeah, so it's slightly different formalism. And you don't really have the same problems with relativity that you had in psychology. You can actually just use the formalism. And so really what you're asking then is, can the concept bat be considered in isolation from boxer or not? Yeah? So we can do these experiments. We've got data, a whole heap of data. So you probably don't want to know about this if you're not from physics. If you're from physics, these are actually, we prime the concept boxer using prime A or prime B. We prime the concept bat using ball or vampire, yeah? So essentially we prime the concept using one or two different sensors. Oh, that's sounding a bit like a measurement angle, yeah? And then we see what word association someone comes up with for the combined concept boxer bat, yeah? So, for example, if I prime someone with dog, and I prime them with, say, vampire, I'd expect to have a higher probability of them coming up with a dog that has sort of a vampire face. Yeah? And so I can do experiments and find out if that's what people do. And I do it with, say, here we've got around 60 subjects, and you can actually find out that things like the Clauser-Horn-Schiminy-Holt inequalities start to get either satisfied in some cases, violated in other cases. So you can actually start finding out which concepts in which contexts are separable, are compositional, and which ones can't be thought of compositionally. So which formalism should we be using here is starting to become clear. Notice this, if you're really sharp, you'll be noticing this is only one measurement setting. So it's not like your standard physics one where you actually get to rotate the whole way through. And this is a big unresolved problem for us. Because language doesn't behave in that same actual continuous way that things like a rotation of an analyzer does, yeah? So that's a big unresolved problem. We're just looking at one bit of space at the moment. Here's another one, decision making. We can add some interference terms and suddenly we know what happened with Linda. We can do the same thing with the sure thing principle. So essentially what we do is we talk about the probability of someone being a banker as being adjusted by some extra interference terms, which could be negative, which then would bring our interference term down, would then bring our total probability down lower. Yeah? So that's how we get the violation of total probability up. Attitude change. You can scale it up, and you could model it for a whole society of people using different probabilities. And then your question of what context you're interested in becomes quite complicated. I've spent quite a bit of time working with some people in CSIRO who are interested in modelling attitudes to climate change. So you think about people's attitudes politically and their attitudes to their friends. They've got sort of a desire to fit in with their friends, but they might have a desire to be true to their own political feelings. And so then you think about how they reframe their attitude towards a problem, depending on the context they find themselves in. I won't talk about that because I'm running out of time. Why is quantum theory a good model? So we've had a very whirlwind tour through quantum mechanics, okay, and through the stuff we've been doing, and I've been doing this for quite a while, so there's a fair bit of work there. And there's a lot of other people working in this area too, so, well, not a lot, but a decent number, so that's a lot of work we've been trying to cover here. My feeling is, but this is still an active debate in the field, it's because of the contextuality of quantum mechanics. So the formalism is contextual, and that's actually where the trick is most powerful. So if you have a system that's displaying contextual responses to measurement, that's an interesting place to be trying to poke with the formalism. So cognitive systems are inherently contextual. They're almost all contextual, which is kind of the problem. Like, you don't really know exactly where the boundary is. And the really interesting aspect of that is cognitive systems or cognitive measurements, we're very, very rarely finding out what was there. It's almost like we're actively interacting with a human when we ask them something. So the very nice example that Wilson and I came up with a couple of months ago was, what do I want to do on the weekend? Oh, I know what I want to do. Well, actually, I'll ask you, what do you want to do on the weekend? You know, you've got some idea in your head. What do you want to do on the weekend? You know, you've got some idea. So it's actually repetitive, like you can keep getting the same, you know what you want. What if I ask you, what does your wife or your husband want to do on the weekend first? And now I ask you, what do you want to do on the weekend? Did it change? Ah, interesting, yeah? So that context, like, it's not that you're just measuring what's there. You're actually actively changing what's there by measuring this system, yeah? That's what's cool about cognitive systems. So, back to the basic question. I'm agnostic. I don't really buy the Hameroff and Penrose argument or those kinds of models. I don't believe, well, I don't care either way, really. I'm just interested in the formalism, right? But, I mean, I think it's unlikely that that hypothesis will work for a number of reasons. I mean, most of them are to do with decoherence. But the thing that I find really interesting is that the complexity of, like, essentially the mind or the brain, whatever it is that we're interested in, and in particular the cognitive processing that people are doing, suggests that these kinds of models can be very fruitfully applied here, yeah? So I don't really care about the underlying materials. I'm much more interested in what the model is that we should be using, yeah? And so, yeah, there's a whole heap of people I left off the list I even realised just today. But yeah, there's been a lot of people I've been working with over the years, and the community itself is a very vibrant and active community. So I encourage you to come along to meetings and stuff. They normally happen in good places. And yeah, thank you very much, Scott, because I've been really enjoying today. It's been very interesting.
Thank you, Rick, and for timing as well. We have time for a few questions, if there are any. Yes, at the back.
Absolutely. So, I mean, the problem is almost how, like, or where, or, so there's at the moment what we've got is a whole stack of different people moving in different directions. And you can see some sort of unification starting to occur, but it's sort of, Yeah, it's a bit unspecified at the moment in terms of how we should do it, and this is one of the reasons for pushing with experiments. Yeah, so the reason for doing these sort of bell type experiments, for example, is that if you can show, say, entanglement as a viable formalism, that's very difficult for a classical model to deal with. Very, very difficult. And in fact, psychology has this concept of selective influences, which essentially derived Fein's theorem for psychology. So, you know, this kind of stuff is being done almost in psychology, and then the question is, which model are we going to push forward through? I think it'll be, my feeling is that it won't be an exact quantum model that applies to the brain. It's actually a quantum-like model, and we need to change probably the group dynamics and the representation of time in terms of the evolution of these systems. But the measurement process is probably pretty good. My other feeling is I don't think we collapse exactly onto a state. I think we sort of approximately collapse. So I don't think that we actually do a genuinely quantum thing as a whole with humans. I'm hoping that sort of doesn't sound too nonsensical, but we can talk after if you like. Might be better, yeah. I completely agree. So I've got a student who's actually trying to model effect, and he wasn't even starting with quantum stuff. He's just doing these computational models from reflective texts, and he's getting more and more understanding of how important context is. It's becoming very important. And the other thing is, this was the reason I got interested in attitude change, because, you know, a lot of those things really come in, like we don't really cognitively reason about our attitudes, we just hold them, and then they affect our decisions. And a lot of our emotions feed into that quite profoundly. But I remember, so Ian Walker is a social psychologist, and I remember sitting down with him and asking him, well, what's the fundamental, you know, what are the bits that I need to model in social psychology? And, you know, we sort of started off, well, it could be attitudes, then it's this, and we sort of went around in this big long circle, and it came down to, oh, they're all important. And emotions and affect and all of that stuff were in that circle. So that problem of how you model the cognitive context with the state, with it all, it's all interrelated. And if you think about it, a state as a vector is almost the basis, isn't it? Like, it's almost the same, like they're both arrows if you think about it, right? So there's almost a nice sort of symmetry in terms of that. In fact, you could think about a state updating or a basis reorientating, yeah? Almost equivalently.
Yes, one there.
That's a good we don't know question. So my feeling is interference is essential and entanglement is essential if you really want to claim it's quantum-ish. Like, well, quantum-like, yeah. Yeah, so the classic thing that Jerome Bussemeyer does is he goes wandering around looking for violations of the law of total probability. So if you've got your total probabilities not summing up to 1, then that's a classic indication of something going on a bit amiss with your classical model. But you can model that classically. And so actually really what you need to do if you really want to claim that it genuinely must be quantum-like is find something like a non-compositional type behaviour, like it has to be entangled in some way. Well, whether you call it entangled or not, like we tend to call it non-compositional for concept combination. So I think that's the weak point, because that's something that classical probability theories have a very hard time dealing with.
One more question? Yeah, let's make last point.
So in terms of the quantum interpretation of what context is, it's very specific. And in fact, there's a whole theoretical apparatus around contextuality in quantum mechanics. It's to do with this Kirsty theorem and a whole heap of stuff there. In terms of psychology and computer science, context is everything that you didn't put in your model. Okay? And that's the difficulty that you're pointing at, right? Now, in terms of, from a systems theory kind of perspective, one of the things, because this is a question that I've been very interested in trying to resolve a bit, you can sort of think of it as, when you identify a system, you draw a boundary around that thing that you're interested in, right? That's your system. And you kind of go, okay, this is my environment. And normally what you do is you kind of measure your system, and your measurement apparatus actually by necessity has to sort of interface between the system and the environment, right? Because otherwise you wouldn't be able to look at it, it's in the system. Yeah? So context is when that interface system is actually affecting the result you're getting out of your measurements of the system. That's the definition I'm playing around with. And it comes back to, there's a diagram back here that I didn't really talk about. This diagram down here on the left-hand side, that's essentially the representation of context that I've been kind of coming towards. So you've got your environment, is that curly E on the outside. You've got your detectors are sort of trying to measure the system. They're trying to measure components of the system. But they're actually interfering with what's inside the system in this scenario, which is how you get that entangled kind of effect out, or the non-compositional effect out. So to me, the context is all to do with the measurement, and that's what I'm fleshing out a little bit.
Thank you very much, Steve. I think it's wonderful that we're seeing a whole new use of the physics formalism that was built up in quantum physics and quantum mechanics. And the book I've chosen, because quantum physics is absolutely amazing and magical, and you're thinking of thinking, the book is The 7 Laws of Magical Thinking.